Welcome to Build with Nas. My name is Nas. I'm the author of the Rebel Open Code repo and the author of developerlife.com, developer website that I've been running for over 2 decades now. In today's live coding video, I've been meaning to this video for some time now. It's going to be all about Rust lifetimes, and it's all going to be, by example. And before we get started, one thing that I really liked is the Rustonomicon discussion around ownership and lifetimes. They have a lot of really great examples and really good stuff to establish a mental model for how to do this. So I wanted to start with that kind of as a guide, and then go through some exercises to illustrate Rust lifetimes in action. So the first thing I want to talk about before getting to lifetimes is references and aliasing. And I think these are some important concepts to really get a handle on before lifetimes are introduced. So in order to do that, let's create a new, let's see, cargo new, let's do this. Actually, is there a fancy way of doing this? Echo, let's do this, echo. Let's see, cargo new. I thought I had a thing for this. It's like echo. I think we're going to do lifetimes xargs minus c. This way, percentage, I think, and percentage. So basically, this will just create a. There we go. Boom. Okay, that was some unnecessary scripting stuff. Let's see. So let's do this in our librs. Let us create our first example. So this is going to be, let's see, example 1 on references. So let's do references first, and then we'll kind of go from there. So there's references, and so this is, we can actually, yeah, so basically in Rust we're really dealing with, actually let's make a test real quick. So we can do test, and we can do example 1. There we go. So in Rust we're dealing with, when we're talking about references, there's some restrictions around the notion of references. So when we create a reference in Rust, it requires us to freeze the referent and its owners. So whatever it is that the referent is and the owners of those reference will be frozen for the scope in which that reference is valid. And in that scope where reference is valid, Rust will not allow us to change the referent and its owners. And I think this one, yeah, actually, I think, let's see, aliasing. Maybe we can look at this one here. Let's see, aliasing. And preferences, maybe that, yeah, ownership is the, I think this is the ownership. If you go through this real quick, it'll kind of give an example for what we're talking about. So let's do this. We're going to do the classic use after free. So, and this is not going to compile in Rust, so I'm not even going to try to do this. But, and again, these are examples to kind of illustrate why these are necessary, and to kind of like get a feel for the nature of references in Rust. So let's try to use after free. And let's say we pass an argument, and that argument will do something and produce a string reference. And so that's what this is. So this is kind of a signature that's kind of like giving us a clue that this is about to happen. So what we're going to do is we're going to allocate some memory here. So I say s is a string, and I've allocated this on the heap, and the pointer to that allocation of the string on the heap, which is essentially a vec of chars, that is in the stack inside of this this function while it's running. So here, if I then return a pointer to or a reference to this heap allocated struct, Rust is going to say you can't do that. And we can't do that because as soon as this code block finishes, this piece of memory is going to be dropped. And when this is dropped, this reference is not going to be valid anymore. So here, since this reference is in scope, we cannot change the owners, so we can't drop it. So that's what this is saying, is that if you want to return this, well, you can't do that. So there you go. Cannot return a reference to a local variable s, and it's returning a reference to data owned by the current function, which means that let's say, if there was such a thing as after return, when this block ends, we would get like a drop of s, so something along these lines. So clearly we can't do that. We can't say return s and then we can't say drop s. That's nonsense. But so essentially the compiler will simply not even allow us to go there. So this won't compile. So that's kind of like one of the first ones. Actually, let's put a little emoji there to kind of drive the point home. So so this is the one of the classic things that we cannot do with the with Rust references. So this is a good thing. Another one is this is this example that's given here where we have a list and we get a reference to something inside of that list, and then we try to change the backing store of that list. Rust won't allow that either. So let's try to do this. So we'll say, and this I'm going to call it try to modify the referent. The reference is the pointer and the referent is the pointee. So here we have referent and it returns nothing, and this is my referent, let's say. We have a vec which contains 3 items. This is our referent, and then let's get a reference to the first item from my referent. So there's my reference. I'm getting the first item. And then a couple things. I have to keep this. So let's say I do this. I say data.push4. Notice this compiles just fine. And the reason this compiles fine is because this has happened. We've dropped our reference to the first item. So, and because that it's dropped, it's no longer in scope, we can happily change the referent and its owners. However, if I do this, if I say, all of a sudden now it's going to break. And the reason for that is that what we're saying here is that while this reference is in scope, which is ref to first item, and it's in scope because we're using it here, we're ensuring that it doesn't get dropped until here, basically. So so what we're doing is that so basically, like, this is we're ensuring the drop doesn't happen until after the print line statement has executed. And so here, because the reference is pointing to something that's inside of the referent, it will not allow us to modify the backing store of that referent. And so that's one of those rules that we just ran into. And so this will not compile. Let's see, firecracker won't compile. So we just have to remove it and then it'll compile. So there you go. That's the understanding before we get into lifetimes and limitations of lifetimes, just to get an understanding of references and the rules around references. And after that, we'll talk about aliasing. After that, we'll talk about lifetimes and so on. Let's see. Now that we have some of the basics out of the way, let's talk about references and aliasing. That's going to be next, the next example. So let's do this. Example 2, we're going to say aliasing. So, and we'll talk about what aliasing is just a minute and how it applies to references. So let's grab some comments. And this is if you look at the Rustonomicon, there's two pieces of content that this particular example will be inspired by. The one is this references, and the other one is aliasing. So you can see it all right here: ownership, references, and aliasing. So let's talk about references and the rules of references. And all these rules are additive. So as we go over these rules, all the previous rules apply, and they will all add up into the lifetime section in just a moment. So let's do this. Let's make a test block, and then we'll say example 2 aliasing. Okay. So here, let's go through this real quick. So there are two kinds of references that we saw in the previous example. We tried to use after free, and we tried to modify a referent. But we just had, like, honestly, the only one kind of reference in this example. So here we're going to introduce a second type of reference. So one is a shared reference, which is what we get when we put an ampersand before something, like we did here, ampersand s and ampersand data. That's a shared reference. Shared references are can only be used, they're read-only. So the mutability here, it's immutable. Anything behind a shared reference is immutable. So a mutable reference, which is ampersand mut, ampersand mute, that's a mutable reference. So we can actually modify the thing that it's pointing to. So it's kind of like two things here. One is that there's a reference, which is a pointer to a thing, and then you can almost think of it as like a shared reference, which means that it's a read-only shared reference, and then there's a mutually exclusive mutable reference, and this is not shared, meaning that we can only have you can have multiple shared references, but mutable references, you can only have one mutable reference at a time. And I'll explain that in just a minute, which is the rules of references. So a reference cannot outlive its referent. So here we saw an example of a reference that was trying to outlive its referent, and the compiler was like, no, you can't do that. So reference cannot outlive its referent. That kind of makes sense. The thing that I'm pointing to, that thing cannot be dropped while the reference is valid. That means if the thing I'm pointing to gets dropped from memory, then the reference should also be dropped. So a reference cannot outlive its referent. Referent lives longer. Okay, that's one rule. Second rule, mutable reference cannot be aliased. This is super important. This is where a mutable reference or an ampersand mute, they can only be one mutable reference. You can think of it as like, this is a bit of a flawed analogy, but if you've ever used read-write locks, you can have any number of read locks, but you can only have one write lock at a time. Same kind of story here. Okay, so a reference cannot outlive its referent, and a mutable reference cannot be aliased. What the heck is aliasing? Aliasing means that we have multiple things pointing to the same location in memory. So multiple things pointing to the same location in memory. So variables and pointers alias if they refer to overlapping regions of memory. So there's a contrived example to actually just kind of show this in a really strange way. So variables and pointers alias if they refer to overlapping regions of memory. So an alias in Rust involves some notion of liveness and mutation. Liveness means, like, is this thing in scope? Can it be accessed? Mutation is that if it can be accessed, if it's in scope, is the nature of that access read-only, or is that nature of that access write? So we don't actually care if aliasing occurs if there aren't any actual writes to memory happening. So this is just a little caveat. It's smart enough that if you're not, you can alias if you don't actually write. So, but we'll see examples of this in this file. And so this is one of the articles, this one, and here's the other one. This is a really good one as well. And this is basically the example that we're going to be using to illustrate this. So those are these two links. So here's a function. It's a bit of an odd function. It receives two references. One is a shared reference, this one, and this is a mutable reference. So input ref and output ref, these are the two references. Now, because of the memory checking rules or ownership rules that we have in Rust, they can't overlap each other, and I'll explain how this works in a minute. So let's say that if this isn't Rust, and I have two pointers. One is a pointer to this chunk of memory, which is a usize, and a pointer to another chunk of memory, it's usize. And according to this, I can write to this the second reference, but not the first one. So if I pass the same reference as an argument to this function, so let's say that I have a variable that I make in memory, and then I just pass the same one as both argument number 1 and argument number 2, they'll clobber each other. Not here, not in Rust, but in non-Rust. Because what I'm doing here is that I'm checking the value of one of the references, then I take the other reference and I modify it. And if I just pass the same reference as an argument, like twice, if I pass the same pointer to this and that, then I've essentially clobbered this output ref, and then moving forwards, input ref is now affected by this mutation to output ref because I passed the same pointer in. So it's like the setup. It's a completely made up setup, which Rust won't allow this to go sideways. But if you read this article, if this was not Rust, then you can see how many different ways in which this can go sideways, and this is why Rust has memory safety is such a huge feature of Rust. So okay, given that we have this function defined, let's try to use it, and we're not going to mess anything up. So we're going to say just use the function, which function, let's see, function, and Rust won't allow input and output to overlap. That means is I can say something like let input equals 10 usize. So I'm saying that, by the way, if the input is greater than 10, the output will be 2. So we say if the input is 10 usize, then I say the output is, let's say, 1 usize. So these are just two different variables that I've made, input and output. Output is mutable, input is not. Then let's get the input address. So this is the let input address. So this will be so this means is that this is the reference, and this is this is its memory location. So we can say let output address, and so it's like this thing. That's the reference. So we're getting the basically just getting the memory address for those references. So reference to input and reference to output. And so let's see. Now we can say we compute. So basically give it the input and we give the output. Now what will happen is once the code runs, the input will be 10, the output should be 2, and these addresses should be different. There's no way we can clobber them. So when you run it, there we go. So test passes, no problem, if you ignore those warnings. So this is we didn't even have to worry about it. The compiler's already taking care of all this, which is why this code just compiles and runs, no problem, and we can make these assertions. So what if we try to mess it up, which we can't, but let's say we try. What might that look like? So what does it look like if we try to clobber input with output? So this is just contrived nonsense. So here's the thing. Rust will not allow any of this to happen. So Kluber. So Rust won't allow input and output overlap. It will not allow them to alias, and Rust will not allow definitely the mutable output itself to be alias. That means we can only have the one. we can't have multiple references. And we'll see that in just a minute. So we say, so here's our output. Notice we just set output as 0 usize, or 1 usize, and then we say, let's put this usize, and then we would say something like this, compute. So I'm saying, run this function, give it a reference to output. This is a shared reference, and then give it a mutable reference to output. So what's happening here? It's read. What does it say? It's saying cannot borrow output as mutable because it's also borrowed as a mutable. That's right. What this is saying is that you cannot have variables and pointers alias if they refer to overlapping regions in memory. So these are both pointers to the same region of memory. This one is mutable and this one is immutable. The second rule, it says a mutable reference cannot be aliased. What are we doing? We're trying to alias this mutable reference, so it's not working. We can't have a mutable reference pointing to this chunk of memory and then have an immutable reference, an alias, also point to that chunk of memory. So basically the compiler never even allowed us to get into this mess in the first place, and it stopped us before we even got started going down that wrong path. So this is will not compile. So there you go. Those are some of the foundational the behaviors of references and aliasing, which we're going to build on next to talk about lifetimes and the limitations of lifetimes. Now that we've talked about references and aliasing, let's actually introduce lifetimes, because lifetimes are the way in which Rust actually enforces these rules. Here are the rules. So that Rust requires any references to freeze the referent and its owners. And that means while the reference is in scope, it will not allow you to change the referent and its owners. And these, a reference cannot outlive its referent, and a mutable reference cannot be aliased. So these rules are actually enforced by the concept or the lifetimes. So let's do this, lifetimes, and let's do that. Okay. So here we have our first example with lifetime. So we're basically going to do the same thing that we did, the same two examples in here. Actually, except that now we're going to use the lifetime syntax to talk through these things. So let's see. So Rust enforces the set of rules that govern how references are used via lifetimes. So they're named regions of code that a reference must be valid for. So, and also when we create a let, each let statement actually implicitly introduces a scope, one of these named scopes. And then for simple programs, lifetimes coincide with lexical scope. So you can think about when the scope that's contained in braces as a way to kind of map to lifetimes. So when regions are complex, not simple, then they correspond to paths of execution in the program. So they can become relatively complicated in some situations. There may even be holes in the paths of execution, as it's possible to invalidate a reference as long as it's reinitialized before it's used again. So there's all kinds of examples of things going in and out of scope, things being essentially shadowed that have an impact on the lifetime. So types which contain references or pretend to use the phantom data, we'll see examples of this, may also be tagged with lifetime so that Rust can prevent them from being invalidated as well. So typically though, we deal with lifetimes across function boundaries, typically not inside a function, because inside of a function we don't have the ability to explicitly name lifetimes. So typically we will notice things like there's a struct and we want to take pieces of the struct. There's actually a thing called splitting borrows. We're going to look at that as well, where you basically take each field of the struct and then you can pass it to a function, and then have that function return a slice into that field. Or you can see in a non-parser where we have like a bunch of data that exists in memory. We provide a slice of that to a function, and that function returns another slice, which is some subset of that slice. So yeah, these are all those are all kind of examples. But before we get too far ahead of ourselves, let's do this. Let's create a test where we're gonna do some simple stuff. Where, let's see, let's make a test here. And in this test, we're going to make a function. And that function is going to do this. Let's see. So this function is going to, this is a function that's not going to work. It's basically, we're going to do this. We're going to do this try to use after free. So we're going to try to make a reference outlive the referent. So obviously the compiler won't allow this, but this is just sort of like syntax that what it might look like. So so in the function signature, we have a lifetime that we have specified. So as like a syntax for generics. So we're saying that this particular function, there's a lifetime that we've defined, and we're saying that there's a parameter that it takes which lives for this long, and it returns something which lives for at least that long. It can live for longer. It can live for exactly as long as take input, but it can not live for anything shorter than this. So what we're going to try and do now is return something that lives shorter than this lifetime. So let's see what that might look like. So one thing we're going to do is we're going to define, so basically code blocks like this in Rust, you can almost imagine that we have a the ability to define a lifetime. So in this case, I'm just saying that this particular block, which doesn't exist, it's just this is not valid Rust syntax. I'm just saying that imagine that this is tickfn. So in tickfn, I'm going to create a referent. So this is the thing that actually, let's say, is a string, and it's allocated on the heap. So this has this is going to be dropped when this function returns. So we know that the lifetime of referent cannot be it's fn, and fn is as long as this function is running. As soon as this function exits, fn this lifetime ends, and so we know that this is going to be dropped at the end of that. So let's make a reference, and the reference is going to be, and I'm going to be extremely verbose. So I'm saying that the reference is, this is again not valid Rust syntax, but I'm saying that this particular reference, explicited, we would say that this reference only lives as long as backtick fn is around. So here, if we now say return reference, this is not going to work. Why? Because the referent, its lifetime is tickfn. Tickfn is only around as long as this particular function, this scope. However, this input it lives longer than fn, because we know that it's passed into fn, which means that it was around before fn was even created, and it's going to be around even after. So we definitely cannot guarantee that compiler, what it's saying here is that the lifetime of this reference fn, take fn, is less than take input, and that according to the syntax, because whatever is returned has to have at least, it has to live at least as long as this thing, or longer. It's saying, or longer. So it's saying that fn, tickfn needs to be greater than, tickfn needs to be greater than or equal to take input in order for this to be valid. So the reference, it lives a lot, lives, you can think of it this way, the referent lives for a short life. It has a very short lifespan, and take input has a long lifespan. So that's why this won't compile. So this will fireworks, oops, firecracker, and then this is does not compile. So that's that. So so obviously this won't compile. So we'll just put unreachable here and comment it out. So yeah, this is an example of how what we were doing in this earlier example without lifetimes, because these were all elided, except for this. Actually, this is a bit of a, I snuck in a lifetime there, but yeah, this is we're kind of like expliciting the rules of references and reference with this syntax of lifetimes. So what can we do, let's say, to make this work? Well, we could make a different function. It's not going to be the same function. So we can say something like function, which is, let's say, fix, try to make reference output referent. So this will be a similar kind of thing, except that we can do something like this. We can say match param. So let's see. So what are we doing here? Okay. So this is clearly a completely different implementation than this, but this is something we can do to fix this lifetime issue. So what we're saying is that the param lives for take input, which is some life that is lifetime that's greater than the lifetime of this entire function block. And we're saying that depending on what the value of it is, we return a string literal. So the string literal, these are all like, if you want to think about it this way, these are all, you can think of it this way, these are all tick static. So I mean, this isn't even remotely like this syntax is made up, but kind of you can think of it this way, that so essentially, actually, why don't we just do this many. So this is basically, you can think of it as because these are global, let me show you. 1 second. This is what they are. I actually wrote up some comments, so I don't have to mess this up by ad-libbing. So it goes the string literals 0, 1, and many. Oops, this is, I think I did this wrong. Let's see, it should be, I think, let's see, it's 0, 1, and many. That's not right. I think I copied this wrong. Let me fix this. I believe that is a bug. This is what it's supposed to be. Okay. So the string literal 0, 1, and many are stored in a special section of memory that's accessible throughout the entire program execution. These are basically globals. This means that these string literals are available for the entire duration of the program. So they have the backtick or tick static lifetime. So that's essentially what this is. So by using these string literals, another way we could have done this is we could have just returned a string. But this is just, I just wanted to show that like backtick static in this case, which is, let's say if it's 0, 1, or many, each one of these is going to live for the entire duration of the program. And the entire duration of the program is going to be greater than the duration of this function. And so the requirement that whatever's returned, it has to live at least as long as tick input is satisfied. In this case, it's going to actually way outlive tick input. Well, unless we pass it a static, string, but it's going to at least live as long as input or longer. So so now if we write an assertion, we can do something like this. And this will basically, this will pass because we're saying, okay, when we run this thing, even though we're passing it like %0, which if you want to think about it, is only valid here. The lifetime of this is quite short, but it's because 0 is basically a global. It's a global variable. So essentially, this will the statement will be satisfied. So yeah, hopefully that makes any sense. So essentially it's tick static doesn't mean forever. It just means like longer than, or as long as the program is running in this particular context, because we're basically creating like these are just globals. These are static globals. Let's see, what else? Oh yeah, so let's do another example. So this one was roughly the try to use after free. Then we're going to do this, so where we try to modify the referent. Only this time we're going to use the lifetimes to describe these things. So here, what we can do is, this is actually a pretty good one. Let's see. I'm just going to copy this whole thing because this is quite complicated. I want to type this out and have some typos. I'll walk through each line of code though. So what we have here is another example where we have some data and we get a reference to the first item in this data, which is a vec. And then while we have that reference alive, we try to modify the referent, and this won't compile. So the semantics, it's like, well, okay, we know that vec is a container, and so it has a backing store, and we know that when we grab a slice into one item in that vec, and then we try to modify the vec, it'll mutate the backing store and then validate that reference. And we're like, how on earth does a Rust compiler reason about this? It doesn't. So it turns out in this example, so here's the example rewritten with these made up lifetime syntax, which doesn't exist, because remember, we can't specify, we cannot name lifetime scopes or scoped blocks inside of a function. We can only do it at function boundaries, like here. So so in this example, it's the same thing. We have data, which is a vec, which is the referent. So when we go to get the reference to the first item, you can almost imagine there's a tick first lifetime scope that's created. So this is made up nonsense. There's no such thing. Again, this is not real Rust syntax. And so so what we're doing here is, when we say ref to first item, you can almost read it as the reference has the lifetime of tick first, and that's what, and we're basically pointing into this vec, and the lifetime of that reference pointing to that first item in the vec. That reference has a lifetime which is only valid in this block. So this first vec tick first, that's its lifetime. And you can see here we drop it explicitly, but we don't have to. But so this backtick first begins here and it ends there. Now, when we go to get this is a slightly different syntax to do that mutation. So instead of doing data.push, just to make it explicit, I'm saying vec : push, which is the same thing. And then I'm passing it a reference to data, this thing. And I'm saying go push 4 into it. And here it's going to complain, no, you can't do that. And it's saying, because you're trying to create an alias for a mutable borrow. And we know that that's not kosher, because we learned here at mutable references cannot be aliased. And aliasing is when you have variables and pointers that refer to overlapping regions of memory. That means multiple things are pointing to, like the multiple things are pointing to the same memory space. Okay. So if you read the syntax, it goes vec : push, and then it goes, we want to create. Remember, we cannot. So we have a mutable reference data already here. It's the variable, and we have an immutable reference into that variable here, which is this one. What we're doing here is we're creating, if you look at the syntax for push, it needs a mutable reference to self. So what we're doing here is that we're generating that mutable reference to self. But that mutable reference to self, the lifetime of that is backtick second, which is only valid for this block. So it's ampersand backtick, tick second, and then mute, and then data. So this string. Notice that this won't compile because it's saying, well, you can't have, you mutably borrowed it, you can't immutably borrow it. So you can't do both. It says you cannot borrow data as mutable because it's also borrowed as immutable. Immutable borrow occurs here. So this is, yeah, it says immutable borrow and then immutable borrow. This is the immutable borrow, and this is the mutable borrow. And it's saying you can't do that. And so the reason you can't do that is because this is still alive when this is created. And that's why the compiler is going to complain. If we had somehow dropped this, then this would have been okay, because then there wouldn't have been any aliasing. But because we need this borrow, we need this reference to be valid until this line, which comes after the tick second lifetime is over. In other words, tick first is always greater than tick second. That's why we can't do this, because this is going to be around for the lifetime of tick second. And that's not okay, because now we have an immutable borrow here in tick first, and we have a mutable borrow here in tick second. So let's review this again. So Rust doesn't understand that this ref to first item, this thing, is a reference to a subpath of data. It doesn't understand that. It also doesn't understand vec at all. So that's good to know. It doesn't know what any of these means, because the compiler doesn't have that level of insight. So here's what it does see. First, a ref, which is this thing. It has a lifetime of, it's a reference to the lifetime of tick first, which is something we just made up. It has to live for as long as tick first, because we need to print it in this line. So that's tick first. This block that I've selected. We know when we try to call push, it then sees us try to make a tick second reference. This is the tick second mute data. It knows that tick second is contained within tick first and rejects our program because tick first is alive for the entire duration of tick second, and we cannot alias mutable references, and thus it doesn't work. So the lifetime system is much more coarse than the reference semantics we're actually interested in preserving. So it's easy to kind of confuse that there's some deeper intelligence to the compiler than there really is, but it's important to understand that these rules of lifetimes are what the compiler is using to coarsely reason about what is safe and what is unsafe, and this can also lead to some issues. But constantly, as the Rust language improves, the compiler is made smarter, and a lot of the more commonly used situations where the compiler can be tripped up, they get addressed. And actually, there's a nice list of this in this article. If you look at the area covered by lifetime, it actually goes into like some more details around this. Actually, let me put a link to this here. So let's see. What should, maybe you can say, is it more info? And we can do this. And we can also do this one. This is another one, limits of lifetimes. This is a great one to this goes in some of those corner cases where the compiler can, it doesn't reason, like our intuition and the compiler's behavior doesn't really match up. So this actually has examples of that. So yeah. In this next example, we are going to use do something that's very common in string parsing or even just non-parsing, where we have we want to do a no allocation slice. We want to provide some input data. We want to use some decision criteria to decide what range of that input data to return and then return it, but not do an allocation. So we're not actually creating a new, like, we're not copying the bytes from the original data that was provided. So this shows up all the time in just about every kind of parsing. So to get started, let's do this. So we'll do mod example for input slices. So, and I have a real world example of this as well. Because now that we've covered some of the theory, I wanted to show a lot of the patterns that where lifetimes show up, and just, it's kind of good to know because it's so common. So before we start, let's do, let's see. Let's do this. We have, oh, I don't think I copied the comments correctly. That's weird. Okay, let's do this again. Here we go. Okay, so we can use lifetimes and slices to work with data without modifying the input data. This pattern shows up with parsers and general string manipulation, and I actually have a real world example here of this is in the Rebel 2 Rebel Open Core mono repo, which has the 2 crate, the Rebel 2 crate in it. And there's a whole bunch of stuff around. Actually, there's not a Rebel 2 crate. This is the Rebel Core. Oh, I see. There's a core trait, the Rebel RS Utils Core, which is not a very good name. But that has inside of it, it's related to all the 2 functionality. It has a code deal with grapheme clusters, and this is a great example where what I'm going to show in this example is a sort of a minified version of this, but please do check this out and to get some more insights. So let's see. So let's create a test, and let's step out the test first. So we're going to provide some data, and the data is going to have strings that are separated by spaces, and we just want to get the middle word. But we want to do it without allocating anything. So this is allocated. This has a lifetime of, let's say, fn, where fn is fn is this block. So this is, you know, if we were to be explicit about it, and this one has so here what we're getting back is actually going to be a string slice, and we don't have it yet, and the lifetime of this string slice is going to be also fn in this case. So, and then there we go. So okay, so let's see what the signature of this function would look like. So if we were, and I'm being extremely verbose here with the lifetime annotations and stuff. So like let's see, let's do this. Rust format skip, so then we can indent this. There we go. Okay, so the middle word takes the input data, which is the lifetime of it is take input. That means it's got to live longer than this entire function runs. Then it returns something that also has the same take input lifetime. So that means that we can't return anything that we've allocated inside of this function. So that rules out the ability for us to allocate something in here and return it if we wanted to maintain this signature, which we do. So let's start by doing this. So first thing we're going to do is we're going to get an iterator for the input, and we're going to basically chunk it by white space. And then let's figure out what the middle index is. So the middle index in this case, I'm going to take this iterator and I'm going to clone it because I need to clone it to count it. So this gives us how many words are in input, and then we just naively divide it by half and return that. So that's what's in here. Okay, so now we have, like, you know, we got the index for bar, which is this one, in this iterator. Because again, the iterator is splitting by white space, so it chunks it into foo, bar, baz, and we just got bar. That's what this did. So now that we have bar, what we want to do, so at the end we want to return a string slice that's slicing, it's a range into the provided input. So here, this is some logic where essentially we're figuring out, like, what's the length of the middle word at this index, and what is the index up until the start of this middle word. So middle word. So that's what this is doing, basically. We just iterate. We just use the iterator and stop at the middle word, and then we accumulate the length up until the middle word, and then that gives us, because we'll need this when we actually do our string slice. So now that we have the sizes, I'm glossing over this because really you wouldn't write this code by hand. This would be like, you'd probably use non-parser or something like that. So now we have the, we're getting the start and the end index using these lengths, and finally we just, this is what I was after. So you can almost like, the reason I did it this way is we can just collapse this so you don't need to see all this noise. But, so here we have, essentially we have, if you want to think of this way, this is also input. So we're basically returning a reference with the same lifetime as tick input. So this is totally cool. This will work, and so this one, if you think about it, the lifetime of original, maybe I should call this data. I think data is a better name. Yeah. So basically data is owned. It lives for as long as tickfn, and then inside of this function we do a no allocation. Essentially, not even copy. We're not copying, we're not allocating, just scanning the input to figure out what the start and end index is, and then we, using this range, we provide a slice of this input, which lives for at least as long as input, because the slice came out of input itself, and that's how this all adds up. So there you go. This is not made up. This is a lot of how sort of no copy functions might work, where you have like a pile of data. You don't want to copy the data. You don't want to clone whatever. You want to slice into that data and then return it, and then you use this as appropriate. And this Unicode stream, there's this grapheme cluster code, and let's see, this one has, it's really good. You should check this out. This is adding support for Unicode string on top of Rust. So this is for text user interface applications. So this is the main struct, and yeah, basically it's no copy because it's really expensive to copy strings, especially when you have like lots of them and you're doing it like multiple times a second. So this is some code that in the real world is used to basically index into a string and turn it into a set of grapheme cluster segments. So yeah, good stuff. All right, and I think with that we're ready to go to the next example. In this next example, we're going to do something a little bit more real world, which is splitting borrows. Like, it's a pretty common use case where you might have a struct with a lot of fields and you want different functions to be able to mutate these fields individually, and you don't want the borrow checker tripping you up and kind of saying that, oh, you can't modify the whole, just a field without modifying the whole struct or whatever. So the borrow checker is smart enough to handle these situations. And so this is actually a pretty common pattern in more, let's say, larger structs. So let's do this. Example 5. What is this? Splitting borrows on structs. So let's see. Okay. So here, let's see. So the thinking is that the actually, let's see, is that it's weird. The mutual exclusion property of mutable references can be limiting when working with a very large struct that has a lot of different, let's say, complicated structs inside of it or enums. So the borrow checker understands structs sufficiently. Say the borrow, let's see, understands to know that it's possible to borrow disjoint fields off a struct simultaneously. So let's put this to the test. So let's call this Let's make a test. Actually, we're going to do 2 of these. So let's try it. Let's start with the first one. So here, let's make a struct. It's going to be very simple. We're just going to have like A and a B field, and they're both use sizes. And then I'm just going to make a function that says change field by reference. So this one, I'm just going to take a field, which is a mutable usize, a reference to one, and then modify it. So where this comes from, it'll be from inside of the struct. So then I can, let's see, I can make a function. So I can say, actually, let's make a struct with just A and B, and then I can say, so this is kind of like the reference to A and the reference to B. So these are now 2 mutable references, right? But these 2 mutable references, they're not overlapping. There's no aliasing because this mutable reference goes into this field and that mutable reference goes into the other field. So even though these are mutable references, they're not overlapping, even though they're part of the same struct. So this is the thing with as the borrow checker gets smarter over time, and I think there's a project called Polonius, which is supposed to make it even smarter by redoing the whole borrow checker. But hopefully one day, as the borrow checker gets smarter, the more common use cases will be covered by or handled, so you don't have to do anything strange. So let's see. So we had A ref and B ref. So and then let's do this. We're going to do change field. There we go. So now we're actually passing a mutable reference to A into this function, and then mutable reference to B. And then we make our assertions. That should be, let's see, assert. That should work. Yep, that works. So that was pretty straightforward. It's just showcasing that it's possible. So let's do this. This is another example we're going to do, and this is a little bit more sophisticated. So I wanted to give an example where there is a struct which itself has a lifetime bound. So this struct doesn't own anything. It actually just contains references. There are actually situations where this happens, like in that grapheme code base that I was referencing earlier in the Rebel Open Core repo. I think the grapheme, where is it? I believe the Unicode string, or is it grapheme cluster segment? One of these doesn't, that looks like it owns stuff. Anyway, there's a bunch of different code examples here where actually it might be here in the Rebel. I think it's in the TUI. Pretty sure it's in here. It's the editor. Yeah. So if we look at the editor engine and editor buffer, let's see. Yes, I think there are, there's code in here which like takes in, I think it's stuff like this, where, let's see, editor component data. No. Maybe it's in here. Oh, that's that one. So editor data. Oh, it's actually in this file itself. So actually, this is not what I was thinking. This is more for phantom data. There are actually structs in this code base which don't own anything. They just hold a bunch of references, and it just makes it easier to pass them around. but I cannot find it here. But yeah, we'll come back to this when we talk about phantom data in some of the upcoming examples. Okay, so let's say that we have a struct, and so far the structs have owned the fields that are in them. So what if we had a struct that doesn't own anything? So itself has there's a lifetime that I put on the struct itself, and I'm saying that let's say I have a useSize field. Let's make that mutable, and I'm making a string, and that's going to be like that. Okay. So here we just created a struct, and that struct doesn't own anything. It just holds a bunch of pointers to other things that are owned by someone else. And the lifetime bound here is tick A. So that's kind of interesting. So let's do this. Let's do an impl block for this struct. And this is an example of a lifetime relation where I'm just telling the compiler, you know, I'm not going to give you an explicit lifetime. You figure it out, which is, it works sometimes. So let's do this. Let's make a constructor. So the constructor is going to return, actually it's going to take in some references. So, and this I'm calling tick A. So this is going to be a string, and it's going to be usize param, and that's going to be a mutable usize. And what it's going to do is, let's see, return oh, that's not supposed to be mutable. There we go. Okay, so we have a pointer to a reference of this lifetime and that lifetime. Okay, and this is compiling so far. So this is saying that whatever the lifetime of the data is, it doesn't matter the constructor. I'm giving that an explicit lifetime. I think if I do, I don't think elision works here. Yeah, it wants some, doesn't like it. So here. So I'm just saying that, okay, this is lifetime tick A, and all of these are of the same lifetime. That means that whatever owns this thing and this thing, when I get a data from those things, the lifetime of this data is got to be it's got to be at least the same. In other words, the lifetime of these things is going to be greater than or equal to this lifetime. So we'll see that in a minute. So let's see, change, let's make a change field 1. Actually, this one is, I think, usize. So let's do that instead of 1. And this one is stir. Yeah. So let's do usize. And this method takes a mutable reference to self. So just basically grabbing it, incrementing its field usize right there. We can do this because even though it's not owned, it's mutable. So we dereference that pointer and then update whatever it's pointing to, which is going to be outside of this data struct. Something to keep in mind. Then we can do change field stir, and here we can do self field stir, and we're just going to hard code this because this is just made up stuff. This works because this is a constant. So the lifetime works out because it's basically static, so it's outlives them all. So let's do this. Let's do so that's our data impl block. Let's do this now. So here you can think of it this: I am in a tick fn lifetime. So here I'm going to say something like, actually, let's do this. So because I'm going to take an fn lifetime here, I'm going to say let. This is where the owned this is where the actual data is allocated. So like, for example, the string param, this is our old value that lives in this lifetime. then we can say, let's see, use size. We can do it a couple of ways. You can say, we can do it like that. So actually, this won't be param. This will be our argument. Okay. So now let's make our struct from these two pieces of data. So what we're saying here is that we want a data struct, and then we want to pass it a reference to old value. Actually, this is just to make it a little bit easier to read. We could just do this. Yeah. The type of use size arg is a mutable reference. So now that we have the situation, we can just go ahead and change the field size, and the field use size, and we can change the field str. And this actually works. And if we do assertions to verify this, so this is actually new value, because when we call change field stir, that gives us new. Oh, actually that should be new value. And then that should work. Let's run it and see. Oh, that didn't work. So this is new value. Wait. Oh, this is. Oops. I want to do this actually. Data. Field use size should be 2, I think, and let's see, stir should be new value. That's right. And this one we can just do this. It's a little bit cleaner to read. Okay. Don't know why this is complaining. Oh, right, because we put the ampersand mute here. Okay, this should work. And yes, it works. So let's walk through what's happening. Like, why does this work? So both these pieces of data, these are owned. Stir arg, use size arg. These are owned, and the scope of it is at the fn block. So basically, this is its own scope, and this is its own scope. This lifetime and this lifetime are all inside of the tick fn lifetime, let's say. So there's 2 other lifetimes here. So we can do tick a, actually we can do tick 1, and we can do, this is tick 2, something like that. So, and this is inside. So, and inside all of that, we have this. So tick 2 is contained inside of tick 1, which is contained inside of fn. So here, when we change these fields, actually, yeah, it's all these references are all valid, because the lifetimes all match up, because this field needs to live as long as fn, and because this is just a pointer to this thing, it all matches up because it's all inside of this block. So this all works. So let me break it. So if I break this, remove all these, and remove this rest format skip. So if I do this, one easy way to break this is if I put, let's say I were to do something like that. So here, it actually stopped working, because what it's saying is that the I'm trying to return something in this struct, and the lifetime of the referent is very short, because it's just this block. So when this block returns, and because the struct only contains references, it's saying that you can't do that. this is going to be dropped. This is going to be dropped, and so this is going to be invalid, and so this is invalid. But if I pull these out and do this, it all starts working again because now these lifetimes all match up. The compiler is not, it's pretty smart that way, in a sense. So now I can call this, and when I do field usize +1, I'm actually changing this thing. Then when I say change field struct and I say field stir new value, I'm actually changing this thing. And I'm just swapping out the value from old value to new value, and these both have a lifetime of tick static. So that all works out anyway, because when this program exits, these are valid at least until that long. So when I run this, it all ends up working for that reason. So this is an example of like a struct that doesn't really own any data. And so when you see structs like this, where they have a lifetime bound on the struct itself, then you kind of have a clue that that's what's happening. And then you have to, the own data has to be managed outside of the scope of that struct. So because that own data needs to be around at least as long as this, the referent has to be around at least as long, i.e. longer than the reference, or not longer, but just as long. It could be longer, but definitely not shorter. And so that's an example of splitting borrows and structs that don't own any data. And we'll do another example next. In this next example, I'm going to be using copy on write, which is pretty inextricably tied to lifetimes because a lot of the usages involve shared and owned data and going kind of moving fluidly between the two of them, where invariably this notion of lifetimes comes up. So I thought this was a good practical example of showing this. So let's see. So we got this one. Oops. I'm using Rust roller for this one. Okay. So I think we can. Does this update copyright? Oh, whatever. Okay. So here we have the copy on write type is a smart pointer that can be used to work with both owned and borrowed data fluidly. So you're not necessarily concerned whether it's owned or borrowed when using this. And the idea is that if you're only reading from this struct, actually from this enum, it's right there, then you don't need to clone it, copy its contents. But as soon as you go to modify it, it'll basically clone whatever was inside of it and give you a owned version of it. And I'll show you this with examples. It makes a whole lot of sense, actually. There's real use cases where this makes a lot of sense. So you can use this in functions where you might need to mutate the argument. And it also is useful when you want to avoid unnecessary allocations and copying. So these are two primary use cases. And so when you are just reading, you don't need to do allocations or copying. When you're writing, then it will lazily clone the mutation or change the ownership as is required. So that's its superpower. So here, let's make a test. I'm going to say example 6, copy on write. And here we have, so it's, that's the standard library. And we're going to make a function that is going to take an input, and the input is going to be a copy on write reference, and it's going to return a different copy on write. And the thinking here is that this function will take in a string and capitalize the first letter of that string and return that. So let's do this. So capitalize, and we have we're going to put a lifetime. This is all superfluous, like noisy, but just to kind of illustrate what's going on. So we have copy on write, and we're saying that the input is going to have, this copy on the cow was going to have like a lifetime of tick A, and its type is this str, and then it's going to return copy on write of str as well. So that's the kind of thinking of this. So we have, actually, why isn't it using Rust format to reformat? Oops, what's going on here? I think it's save, update copyright reformat code, and that's weird. Let's see, Rust cargo check, rest format. Oh, okay, that's weird. Okay, very strange. All right, cool. Okay, so here we have capitalize, and so what we're going to do here is that if the input is empty, we're just going to return input, which is, it doesn't violate our contract with this function signature, which is great. So you can see if the input is empty, we can't capitalize, there's nothing capitalized, so we just return what we got, which is this reference. So we just return the reference. And that all works because this reference is alive for the same duration as this, because the lifetime is the same. So this is totally cool. And this input is allocated or owned in a scope that's outside of this function. So there's a different scope in which it's actually allocated. And then we're basically working with a pointer to whatever that owned data is in this function. So let's do this. So we say if the input chars, and this is like if it's all uppercase, then we just return input as well, because it's the same thing. And then this must mean that if we arrive here, that we're going to have to lazily now do this clone thing. So we do, we say, no, we don't say input to string. We say string. We're going to create a new string of the same size as the old one. We're going to do cloned push stir, and here we're going to put input. Just we're going to slice it. Just, you know, there we go, to uppercase. And then, actually, let's put this to do. So yeah, so far so good. And then, actually, we can just do this now. So whatever this clone thing is, we're going to return it. So we're going to say, oops, no, not that. We're going to say it like that. So this is, let's see, so we got clone, and then push string, that's the first letter. Then, actually, this one is not too lowercase, it's just that. And then we return the, notice that this variant is the owned variant because it's an enum. So we got the borrowed variant and the owned variant. We don't know what variant it is when we receive it, but we do know that when we return, at least from this code path, that's code path 1, 2, and 3, we know that it's going to be essentially whatever it is, it's going to be converted to an owned version of it, and then that will be returned. And notice that this is fine. The compiler isn't complaining. Let's see, is there in Zen mode? The status bar. That's weird. Oh, we're in presentation mode. That's why. Well, I guess I could do this. Zoom. IDE to 125. Okay, that should work. Okay. Just like this. All right. So. Yeah, that works. Okay, so here we have also in Rust Rover, they just recently created a new terminal that I'm really excited about. Let's see, the old one from IDEA needed a lot of, it hadn't been updated in a long time. So I think this is the new terminal. Where is it? Where is it? I think it's in like UUI or something. Okay, I don't know where it is. New term. I enabled it somewhere. Nope. I think it was here. There it is. Enable new terminal. Oh, it's under settings. Tools terminal. I see. This one. It's really cool. It has a lot of nice features. Okay. Okay, so let's see. So now Okay, so now we have, because it's owned, the lifetime of, the reason this works is that we're not leaking anything. You might be wondering, okay, aren't we leaking because we're returning cloned out of this function? Well, no. Yes and no. I mean, we're not leaking because what we're doing is we're telling this, we're basically returning a different enum, and that enum, actually that variant, owns this thing. So this enum is not a reference. It's just an enum. It just so happens that the enum can either contain a reference or it can contain own data. So now we're actually converting it to own data. So you can just say cloned or owned or whatever. Let's see, this is owned. So, and so actually I'm just going to turn it back to cloned. I think that was cloned. Okay. So this copy on write enum actually owns this data, and we return it. We don't return a reference to it. And so the lifetime of what's returned is as long as this is. So that's kind of like how this magic works. It's pretty awesome, actually. It almost feels like we're defeating the bar checker, but we're not, because what we're returning is actually a new enum. It just so happens that enum can contain a reference, or it can contain an own version of that type. So very clever. So this is an example of like, if you start with like some data and you don't know if you're going to have to mutate it, you can kind of take this approach. So this one we're not really mutating it. We're like, when we're going to modify it, we're returning a new owned version of it. So let's see this in action. We say we borrowed data. We have cow borrowed hello, and then we do owned data, which will be cow owned, right? And then oh, and then this one is it doesn't know, so we can just do, instead of this, we can just do string from. That preserves the type. Okay, and then oh no, that did the same thing. So let's do this to string. Okay. Sure. So this is cowster. Okay, let's just explicitly put that there too. Cowster. Okay. That made the compiler happy. And then we have, now we're gonna call this function, and we're gonna say capitalized borrowed data. So that's this is a cowster, and we're getting we're basically calling capitalize with this borrowed data, and then it works, and we can say capitalize own data, and that works too. So we don't particularly care if it was owned or borrowed, since we're using cow, and also the lifetimes and everything just match up. So this is pretty incredible, because here, if you notice, we're just returning the input. We're not modifying anything. Also returning the input, not modifying anything. But here we're actually, in the case where these two branches don't match, then we are actually creating a new string and then putting that in a cow and returning that. So that's pretty cool. And then the lifetimes all match up. So let's see. Because this, whatever is returned, this is going to be allocated somewhere, and when this thing is dropped, then this will be dropped. So we don't have to worry about it. So that's why there's this underline here saying that, how do you do this? This one actually, we can actually elide lifetimes. So there's no need to be explicit here because the compiler is smart enough to figure it out. But we'll just leave it in there because it's just, just is fine. So let's see, assert, then we do finally. So that's going to be hello, and this is going to be world. So this should work. Let's run it and see. Did it pass? Yes, it did. Excellent. So that kind of works as expected. Nothing. What is this? Oh, borrowed. Typo. Okay, so that's an example of us. We're not modifying input. Notice we're just taking an input and we're returning a different cow. But what if we wanted to modify the input? This happens sometimes where you want to pass an argument. Most of the time it's going to be read-only, but sometimes you want it to be write. And when it's write, you want that argument that you pass to a function as a parameter. You want to use the value of that argument down the line to do something, to do some other logic in your code. So essentially it's a mutable, it's a mutable argument that's being passed, but we're wrapping it in cow because if you're not going to mutate it, if you're only reading from it, then we'll leave it as is. This is a lot of efficiency gains from not having to do any allocations. So let's see, cow 2, and here we can do same thing, and that is not right. What we are going to do is we're not going to return anything actually. So we're just going to do, I just wrote this. This is just noise. So what we're going to do here is that we're going to capitalize mute. So that means that we're not returning anything, but we're actually going to mutate potentially the input. And so this is going to be a different type. It's going to be a mutable reference to copy on write. So here we're going to do the same kind of thing. If input is empty, we return. If input chars, they're all uppercase, we have nothing to, actually not upper. Actually, it's not all. It's really like is that a thing? No, that's not a thing. Okay, so we can say return if the first character is already uppercase. Let's see if Copilot figures this out for us. Oh, I see. Sure, why not? So let's see if input next unwrap, return input, and okay, so does this run now? Let's see if this test will run. It does. So it's actually really capitalize first there. Just to be clear, this is empty. This is, let's see if, unwrap is uppercase. Sounds good. Return input. That's fine. I mean, we're not really trying not to use unwrap, but that's okay. It's like if we can do something like this. If let something like that. So if the first char is uppercase, we return input. Okay, and else we just do this, go down this path. So this is better. Okay, this should work as well. Okay, cool, great. So now let's do this. So we're not going to do this. We're going to say basically just copying the same code. It's exactly up until this point it's the same, except there's no return. So we just say return because if there was any need to make a change, we would just mutate the input, which is interesting. So let's do this. So now this part is very similar. We just we do that. We do this. We do that. That's the same. But the difference is right here. So what we're doing here is that we're saying, okay, dereference the pointer that you gave me, that I receive as an argument, a parameter in this case. Take this parameter and then dereference it, and then now put this in there. So that's how that works. So and the lifetimes are all good because this is gonna live at least the compiler can guarantee it's gonna live for at least TK. And this is the same thing. We can just elide the lifetimes. This is absolutely no reason to put all the stuff in here, but I just did it just to be verbose. So here, let's see, now that we have capitalized mute written, so we're going to do, we're going to have mute. Notice that this is now mute, so it's no longer just borrowed data because of this function signature. So, and then we're going to do let mute, mute data, and we're going to say world. Okay, so far so good. So now we're going to call this function with the borrowed data and the own data, and notice that the compiler's still happy. And so we're going to say this and that, and let's see if that works. Yes, the little green check, so that worked. So what happened here is that the difference between these two is that here we have a function that will not modify or mutate the cow that's passed in, and this one is one that will mutate the cow that's passed in. But if there are situations where we don't need to mutate it, then we just simply do a return. And input is as it was. But in situations where we do need to mutate it, we clone it, and then we stuff it in a we dereference input, and then we stuff the owned enum there. So again, very clever, beautiful pattern. This it's a thing that shows up all over the place in the Rebel 2e code base. There's tons and tons of examples of using copy on write. So yeah, it's a good one. And with that, that's example 6. In this final and 7th example, we're going to take a look at something called subtyping and variance. There's some sort of intuitive feel that we might get for lifetimes that will cover us most of the time for most cases, but there are some situations where there's some corner cases, and discussion of subtyping and variance kind of gets to the core of that. So this is an excellent excellent read on the Rustonomicon, and let me actually walk through this real quick. So let's create a new example for this one. Let's go to librs, mod example 7, and we're going to do this as subtyping and variance. Subtyping and variance. There we go. Okay. So let's start with some definitions for this. Okay. So in Rust, we have this. This is kind of a sort of related. There's something copy and clone Rust. Let's do this. Nope, this one. So if we look at the copy trait, this is not directly related. So the copy trait, this is a super trait. So essentially, it's like a superclass. It's not really inheritance. It's more like it is sort of inheritance, where this is, if you want to think about it, this is this is superclass, and this is the supertype, and this is subtype. And so what this means is that copy has all the requirements of clone, but clone does not have all the requirements of copy. In other words, clone has a certain set of requirements, copy has even more. So that's kind of like what this is. This is a subtype, and that's a supertype. So, or in this case, a trait, super trait, and this is a subtrait. So this is kind of not directly related, but it kind of gets to the notion of subtyping. And we're not talking about subtyping like we did for traits, but this is subtyping for lifetimes. So let's say that sub is a sub is a subtype of trait, and in the syntax, let's just use this the same thing that we saw in the trait syntax here. Where is it? Something like that. The sub is on the left and the super is on the right. So with that, when we see something like sub colon super, that means that sub has more requirements than super. So it's suggesting to us that the set of requirements that super defines are completely satisfied by sub, but sub may have more requirements. That is, in kind of like squinting, looking at it, you can think of it this way, that sub is greater than super, sort of. So replacing those lifetimes, so let's say that you see tick long colon tick short. That means that tick short, whatever it is, it's included in tick long. So tick long defines a region of code that completely contains tick short. Tick long may define a region that's larger, and that's okay. So it completely contains this, completely contains that, and this might have more than that. So that is, tick long is greater than tick short. Okay, so with that sort of working definition, we're not going to talk about variance first. Let's talk about subtyping, which is the sort of the beginning to all of this. So let's do this. Let's make a debug function, which it's just going to take a lifetime A and a type of T, which implements display. So that means you can print it and it's not sized. So, and that's that super type thing. This is the super trait. So T is the generic type, and like, you know, it has to satisfy these trait mounts. Okay. So this one, sorry, this one is just the generics, and then we say the argument can be a reference to T and another reference to T. So in other words, given two pointers or two references, we're just printing them to standard out is what this is. Nothing too interesting. So, okay, so here the lifetime tick A is the same as the lifetime. These two, A and B, have the same lifetime, tick A. So in order to demonstrate subtyping, what we're going to do is that we're going to create two different variables. This one is going to be hello. This is going to have lifetime of static, tick static, and then we're gonna make a shorter lifetime, and this one's going to be we can say something like, literally just create this, and we can say, so hello, and world is, we're going to say toString, so this is owned, so the lifetime of this, you know, it's within these curly braces, and then we're going to call debug world with hello. And let's see, oh, sorry, not this. Oops. Debug, what am I doing? Hello and world, but the world is going to be a pointer. There we go, reference, I mean. Okay, that's what I meant to type. So, because hello is a reference already, and world is also a reference. So this works, but why? If you think about it, they actually have different, if we put this in two separate lines, so let's do this. If you think about it, the hello has a different lifetime than world. But how come debug is able to somehow not have a problem with that. Like there's no compiler error. So there's warnings, but no compiler error. So why does this work? This is odd. Or is it? So the reason it works is because of subtyping. And what we're kind of saying is that if you look at these two lifetimes, this is, you can think of it as long, right? So you can think of this as long. I mean, it's not really true, but just imagine instead of tick static, it's tick long, and this is tick short, right? So we know that tick static or tick long completely includes tick short. So that means it spans more than tick short. So what debug does is that because of the subtyping, it just downgrades the static to short, and then this is satisfied, backtick A. So essentially what's happening is that the the reason this works is because even though the reference tick statics string is a subtype of short, the references are compatible. Even so, and there's a reason for this. So so it's kind of like if you kind of sort of use your intuition. Okay, well the lifetimes are compatible, so then maybe the references are compatible. In this case, it's true, and for most cases, it's true. But there are certain cases where it's not true. So that's why we have to dig a little bit deeper into variance. So subtyping, it holds for the lifetimes, and it even holds for, like, super traits and stuff. But when things get generic over types and lifetimes, then variance comes into play. And this isn't necessarily so we glossed over the fact that tick static, which is the long, is a subtype of B, which is short, and that it is implied that reference for tick static is a subtype of basically of type T. That we're saying that the long and the short lifetimes, it doesn't really matter because they can just, like, because of the subtyping, they're equivalent. That means we can downgrade them, and it's the same. It's equivalent. So that's great. That does work. But if we change this signature of this function to something else, then it'll break. And before we do that, now it's the time to get into variance. This table is really, really good. It's a table of generic types and their variances. This is kind of an important table. So let's like dig a little bit deeper into this table. So if we look at the function debug and all this stuff, this just means this is T. So in our example, where it goes, there's lifetime and T. So essentially, when we see a signature like this where there's a lifetime and a T, we can have different lifetimes that take the place of tick A. This is a parameter, but you can imagine it being replaced with an argument, which is tick static or tick short or whatever. T again is a type, or in this case it's a type parameter, so you can imagine it being replaced with a type argument, whatever that is, in this case str. I think in this example, yeah. Notice that it doesn't say str here, right? It just says that the T is whatever, anything that has a trait bound on display and may not be sized, not a requirement, and that's how we can and so that's the trait bounds for this one. Like if we remove this won't work. Actually, yeah, it doesn't work because it's saying blah blah blah. Stir is not sized. So maybe do that, and then it works. Okay, It's like type erasure basically. But yeah. So essentially, when we're looking at these tick A here, that's coming from here. So this can be tick static, it can be tick short. This we know is just str. So that's not that's what the type is. So using this table, the way we kind of read this table is the following. It goes, and I have a small version of the table here because that's kind of long. So this is the, let me see if I can make this bigger. Nope. Unfortunately, I cannot make this window. Oh, yes I can. Oh, a little bit bigger, whatever. So here we have, since tick A of t is covariant over A, and we know that because if we look at tick A of t and then we see the column for tick A, this is covariant, and we look over the column for t, it's also covariant. So this means that whenever it's covariant, we're allowed to perform subtyping. And so when we see, let's say, tick A of t, and we see two different tick A's, like not tick A's, we see like tick static and tick short, as we are seeing here. Like when we pass the arguments, this is going to be tick static and that's going to be tick short, as you can see down here. Then what this means is that because they're covariant, subtyping is allowed, and because subtyping is allowed, just like let's say static or long, static is a subtype of short. That means static includes short, and we can downgrade. Let's say there where we basically where we can use short, we can use static, because we know that static is short. So if we can pin it to short, that static, any static will work, because we know that static is a subtype of short. So that means whatever holds for short, that'll hold for tick static, because of the sub and supertype relationship. And because they're covariant, what we can now say is that not only can we say that these lifetimes are equivalent, because this is the subtyping holds, it means that when we have a reference, then the references also exhibit the same subtyping behavior. So a reference of lifetime tick static is equivalent to a reference. In other words, this reference is a subtype of that reference. This concrete type is a subtype of that thing. So wherever we can use this thing, we can use that thing. And that's exactly what's happening here. The compiler is downgrading the tick static into a tick short. So, kind of makes sense. Like short means, and you can think of it as tick static is like long. So it's like something that lives longer than short. So if it lives, that means we know this is going to live at least as long as short. So so the lifetimes can be subtyped, and now because of the covariance rule, the references can also be subtyped. But if you notice in this table, there is one I, or invariant, and that's the next example that we're going to look at. So this is a mutable reference with a lifetime is not covariant over t, it's invariant. So what that means we will discuss next. So let's do this next one. So this one we're gonna make variance, and this one, let's do this. We're gonna have a similar function, but it's gonna be a little bit different, because in order to trigger the invariant, this thing I, which if you look at this table is this one. So in order to trigger this, what we need to do is we need to have one argument that's a t, and another argument that's a mutable reference to t, to demonstrate this. So here I have a reference, a mutable reference. You can say mutable reference, or mute ref. So I have a mutable reference and I have a value. So the mutable reference is ampersand mut t, and the values of type t. So according to this table, because ampersand, or whatever actually let's put a lifetime in there too. So let's do this. We can do take A and we can do take A. I mean, it's unnecessary, but just to be verbose, let's do it. Take A, take A. Okay. So here we have, actually, let's just do reference. It's a little bit cleaner. Okay. So we have a mutable reference to t, and then for a given lifetime, and then we have t. Okay. So, I mean, the compiler doesn't say anything right now because we haven't released this function. But let's do a similar kind of thing that we did the last time, where we're gonna have a mutable reference of static lifetime, which is hello, and then we can do. Don't know exactly what happened here. Let's see, hello, and it's a static and stir, and it is hello. Okay. Then we have that same sort of thing. We have a short. Let's see here, and then inside of the short, let's do this, and let's do world in here. So let world equals world toString. So, oops, and then we're just going to call assign. And as you can see, this is not going to work. Oh, that's because the signature is wrong. Ugh, sorry. This is ampersand world. There we go. Let's see what error we get. Nice. Exactly. So we're getting a problem. It's saying you can't do this. This is not, the type is not, there's something wrong with these types. Essentially saying they're not equivalent, just like they were here. Even though the, short is still a subtype of static. This is static. And short is still a subtype of static. But for some reason, this isn't working. So if we look at assign, let's see, why isn't it working? So the reference is of type. So here we've hit upon invariance. Invariance means that given a reference like this, a mutable reference to t with the lifetime of a is invariant over t. What that means is that this is not the same as t. They cannot be covariant. Means they're equivalent. So this thing is equivalent to that thing. This thing is not equivalent to that thing. And so the way we see that is that if we were to break down this function call into two lines, we have here the hello is really a mutable reference with a lifetime of static, and world is an immutable or shared reference. Really, this is mutable reference is a shared reference to let's see, oops, let me see. Yeah, so this one is a mutable reference, this is an immutable reference, and here we have what is this? Yeah, so this one, it's ampersand mute and then tick static. That's the first one, the reference. And the second thing is the value, which is world. That's just straight up, and it's a reference to let's see. Sorry, I think oops. Yeah, that's right. Ampersand. I think that's correct. Okay. So here we have, okay. So let's see. 1 second. Okay, so I think this is correct. Let me make sure that I don't have any typos. There we go. Okay. So these are not equivalent, and so this this function let's go dive a little bit deeper into the function. Actually, this one has that example too. Actually, this is the input and value, and they are not equivalent. Exactly. So, because value t is str, this is ampersand mut str, and then this is str. So, this is the problem. Yeah. So, so here, what is happening? Like, why doesn't this work? Well, we have two things here. What is, let's see. We have two different lifetimes. One is tick static, and the other one is tick short. So tick static is a subtype of tick short, which is true. This is tick static, and but this holds true, but what doesn't hold true is because of this invariance rule. It means that so this function, which just takes a mutable reference and a value and overwrites a referent with it, it says in the signature that the referent and the value must be the same exact type. So this one, this t. So, but how come, but you know, isn't it the same time? Isn't it str? And the answer is no, because the actual type is this thing. Reference of lifetime tick A, which is a mutable reference to t, and this is just t. And so because yeah, exactly. So basically, because what it means that this tick, actually it's tick A, not tick A, yeah. So tick A mut is invariant over t, means that the immutable reference of lifetime, oh, actually it said it right here. Never mind, this is actually correct. So a mutable reference to, let's say, a lifetime of long or static of t, of type t, is not a subtype of that same thing, but just change out the lifetime to short. Even if the lifetimes, let's say, they're related, even if the long is a subtype of short or static is a subtype of short, the mutable references are not, they're not equivalent. So that's what this invariance is. So so that's why when we go to make this assignment, it doesn't work, because these are not this doesn't fit this. So because we have, the difference is that we have two different lifetimes. So when we actually pass in a reference to the first argument, this, you know, it's like ampersand tick static mut and then str, that's hello, and world is ampersand tick short str. So that's why, or just that's why it's not working, because those references, the t and the reference, the mutable reference, they're not the same type, and so we cannot use one where we can use the other, and there's no substitution that's possible. So so basically this doesn't work, and there's like a ton of detail in here around like analyzing each line at a time. So yeah, it's basically ampersand mut t is invariant over t. So compiler concludes it cannot apply any subtyping to the first argument. So t must be exactly tick static str, which it isn't, because in our case it's tick, one of them is tick static str, the other one is tick short str. So, and which is different than this one, because here we put the t, you know, the t's are the same, and it works out when we weren't making one of these mutable, because those are covariant. So the covariance helped us, because even though in the previous example here, A and B were, let's say, the same type, the reason we could pass two different lifetimes is because ampersand t, sorry, tick a, the reference of lifetime tick a to t is covariant over that lifetime. So we are allowed to perform subtyping, and which is what we did. We used the fact that static is a subtype of short, and that's how we were able to get this to, this compiles no problem. So the compiler decides that tick static stir can become, in our case, tick short stir, if and only if tick static stir is a subtype of this, which will hold if the tick static is a subtype of short, which it is. So this is why this code works, because it's covariance right there. But it doesn't work here because of one of the arguments is a mutable reference. That's why. So because of the contravariance, or sorry, invariance, because the invariance, they're not equivalent, so we cannot do that substitution. So let's see, and yeah, so that's basically that's roughly what we see here. This is it's kind of a really long and detailed explanation, which I think is worth going through, but I just wanted to sort of summarize it to some degree, so hopefully this makes sense. Yeah, so there we go. Meanwhile, in the caller we pass mutable reference with a static lifetime of stir, and this one for us is I think we called it short, not world. Yeah, so it's like short ampersand, it's an immutable reference of lifetime short to stir, and because mutable ampersand mu t is invariant over t, we see it right there. Actually, we don't have to write it this way. According to, in this table, it just, there's no lifetime. Oh, actually, sorry, there is lifetimes. Never mind. So, where'd it go? Assign. Yeah, so ampersand mu t is invariant over t, so the compiler concludes that it cannot apply subtyping to the first argument, and so t must be exactly ampersand tick static stir, which it isn't in our case. So because in our case, when we look at this, since this is covariant over tick a, we are, oh, sorry, this one. Okay, so okay, actually there's a typo I just noticed. Let's see, I think up here, where is it? Mute. I think I had mute up here. Yeah, I think I had, wait, where is it? Variance. Yeah, this is a typo, I think. Let's see, it's not a subtype of, I think what's happening here, this might be useful. So here we have, let's see, mute, tick static, short. Aha, that's right. That's not right. So this is actually just that. Okay, so essentially what's happening here is that the type of T is actually a tick static stir. So it's a little bit confusing. So here we have, actually this is not mutable. This is not correct. This is, let's see how many other places I've used this. Oh, just here. So this one is not mutable. Okay. So we have, what's happening here is that on the left-hand side, we have ampersand mute and then tick static and then stir. So this is ampersand mute over T. So T is actually this thing. And so we have where you can say T equals exactly. So tick static stir, this thing. And so this, whatever this is, the thing on the right hand side, tick short stir, is incompatible because it's expecting the only, so if you want to think about it, this is the ampersand, so this is kind of like, which is ampersand mu t, where t is this expression, and this is on the left hand side, or the first argument. This is argument number 1, and argument number 2 is of type that we're giving it this, and it is expecting t, which is not, oops, no, that's not right. It is expecting, actually, let me just copy this again so I don't mess it up. It is expecting this expression, and as note, this expression is not that expression. And they don't match. So this is first argument, and this is the second argument. These don't match. This t does not match, and that is why the compiler has a problem. So mute lifetime static stir cannot be a subtype of that. That is correct. So if you look at this table, it goes this thing, or the t is this expression. It was a little bit confusing that t is actually that. So yeah, so that's the ampersand mu t is covariant. So let's say we can put this here, and I think this will make more sense. So this is the, I think, in variance. So so we have ampersand mu t is invariant over t, meaning that ampersand, oh, no, that's not right. There we go. Meaning that, actually, we can just say t. And this is, yeah. And even if this holds true. So, of t. Yeah. And actually, this doesn't make any sense. We can just say, and we can just leave it at that, actually. There we go. So, ampersand mu t is invariant over t, meaning that these are incompatible. So we have what is this? Oh, there we go. So we have the first argument, which is ampersand mute, and then take static stir, which is the t is ampersand take static stir, and the second argument is t, which is take static short stir, not take static, sorry, take short stir, not take static stir. So the lifetimes are incompatible. This expression, the lifetimes are incompatible, even though that's exactly, this means that that's exactly right. So cannot be a subtype of this. So this don't match up, and even if static is a subtype of short. There we go. Whew, that is very, very complicated to explain. There we go. So this, I think, makes more sense. Excellent. If you haven't already, please subscribe to the channel. That helps. Well, it helps build the channel, and also it helps me build the channel. And also, you'll get notified when new videos, when I record new videos and publish them. Additionally, if you go to developerlife.com, you can also subscribe for updates. So usually when I publish a video, I'll create an accompanying blog post or article that goes along with it, and a repo. So the repo typically for these is in, I think, here. So Rust Scratch, which there's a bunch of, I think some people have started. So this is usually like sort of like a experimental area for repositories. This is a good one to take a look at as well, and they're all related. So yeah, please do subscribe. I don't publish that. I don't send out that many newsletters. Maybe like every time a video drops, so maybe once or twice a month. And then we also have a Discord, and the Discord is a good place to ask questions, give feedback and comments. I usually disable comments. I disable comments on all social media, or I tend not to read them, because you never know what you're going to get with comments. And even though there might be a lot of positive ones, a few negative ones don't really make it worth reading. So if you have any comments, please go to our Discord and share it there. And if you have any questions or requests for other content, with that, that's the end of this video. And thank you for watching, and I'll see you in the next one.